All right, so now we're going to continue off where we left, where we have introduced this module, chemical engineering thermodynamics 2. Remember, the unit that we are doing is called volumetric properties of pure fluids, right? So now what we did here is we looked at the outcomes, right? We did an introduction on this topic, and then we also looked at the major definitions and explanations, whereby we looked at the system, the closed system, the open system. We looked at the interface, whereby it is the phase that separates two phases, which is phase one and phase two. And then we also looked at the thermodynamic properties, where we have the intensive property and extensive property. Like I said, the most common one that we're gonna focus on for now, we're gonna look at the pressure, the temperature, which are intensive, right? And then we're gonna look at the volume, which is in this case extensive property. And therefore, we looked at the homogeneous and heterogeneous systems. And then we defined what is a pure substance, right? And then we looked at how to see a pure substance and what is not a pure substance. And then we also looked at the examples of pure substances. And then we also looked at the phase changes, right? Not the phase changes per se, but different phases and how molecules or atoms actually behave in each and every phase or in each and every state. So now today what we're gonna do is we're gonna learn more of phase changes, the processes of phase changes, right? Um, why we the first session, right? It was all about the introduction and what is a pure substance. So this is where now you're gonna be able to interlink the phase changes, those phases, liquid, solid, and gas. We're gonna combine them along with the properties that we have learned, right? And then we're gonna learn more about the pure substances. How do they behave under those situations? I mean, like for example, there are numerous pure substances out there, isn't it? So in that case, that means they also behave differently, right? So we're gonna examine how these pure substances actually behave under different properties such as intensive and extensive properties. We're going to look at the pressure, we're going to look at the specific volume, we're going to look at the temperature and how these actually correlate with one another, meaning what's the relationship amongst all of these properties, right? So without wasting any time, let us just go through this. Now, what we see over here, we have diagrams that are very, very, very important. And you need, by just looking at them like this, you should be able to explain what is happening in these diagrams, right? So I'll be explaining only these diagrams with no notes. So buckle up and make sure that you listen attentively and you take notes of what I'm gonna say, and I'll try to give you notes here and there so that you can understand how these diagrams actually work. Okay, so these diagrams, all of them, it's the same thing. Okay, it's the same thing, but presentation it is different. For an example, you can see that in this diagram on this side, we have the temperature. On this graph over here, we also have the temperature. We have the volume. We also have the volume on this side. So you can even tell that these two diagrams are exactly the same. It is just that the presentation is not the same. But how can I see that this diagram is the same with this diagram? So if I extract this portion, this only graph over here, it's gonna be exactly the same as this one over here. It's just that now we have different lines over here. I'll explain what are those lines, okay? Okay, by the way, we call them the isobars, okay? They maintain pressure throughout, meaning the pressure is the same throughout. Call them the isobars. So in this case, looking at this line, looking at this line, looking at this line and this line and this line, the pressures are not the same, right? So if the pressures are not the same, therefore, that's why we have these different lines. But we'll explain that much more better when we get to this diagram, by the way. So what I want to do right now, I want to start explaining thoroughly and depth of this diagram that I have just marked with an asterisk over here. How does this diagram actually work? Okay, and then here it's just a correlation between the saturation pressure and saturation temperature, but I'll also come back here to explain it much more better. So if you understand these diagrams, how they work, and you have an understanding and the terminologies that are associated with these diagrams, let me tell you this, you understand everything, okay? So now let's see how to go about to understand these diagrams. So in this case, remember, we're going to look at the vapor, liquid, solid phase equilibrium in a pure substance. And remember, we are talking about the pure substances. We are not talking about any other different substance. The substance is supposed to be pure. For an example, a mixture of water and the gas, right? We have a pure substance. Water is a pure substance. So that means the good example that we're going to use to understand how does the pure substance actually function under different temperatures, pressures, and specific volumes, we're going to use water. Okay, we're actually going to use water. So now in this diagram, we have three diagrams. We have A, B, and C. And we see that there are transformations amongst these diagrams, right? So what do we call this container that we see over here? We can just call it a cylinder, right? Or we can just call it a piston. So because it has this, what do they call this? This some sort of a stopper, or call it the stopper, or even call it the piston. So this actually is there to do what? To trap the molecules or the matter not to escape out of the system. So having a look at diagram A, it represents a system, right? This is thermodynamics. You have to understand that we're going to work with the systems. So everything that is outside of the system, as much as we defined it at the beginning, it's going to be the environment that is outside of the system. So we want to focus inside of the system. And then, by the way, it's important to understand whether the system it is open or the system it is closed, because that's very important. In this case, we can see that our system it is entirely closed, right? Why? Because the piston, this stopper over here, this compressor over here, nothing escapes out of this system. That's very important. Sharp 5. So now, this is the first thing that we're going to look at, the diagram number A. So now consider a system, 1 kg of water contained in the piston cylinder arrangement shown in the figure below. This is it, right? And then suppose that the piston and weight maintain a pressure of 0.1 megapascals in the cylinder, and that the initial temperature is 20 degrees Celsius. So in this container, what's happening is state number 1, it's a first state, right? It's a state function. So in this case, our temperature, which is our property, intensive property, it is 20 degrees Celsius. And therefore, what is the pressure inside of the container? Another intensive property, the pressure in this case is going to be 0.1 megapascals. Right. Okay, sharp, fine. We have water. We just use the thermometer to read the temperature inside of this water. We find out it's 20 degrees and the pressure is 1,1. Maybe if we use the pressure gauge to measure the pressure inside of there, then what? What's the next step? What are we actually going to do now? This is what we're going to do, right? We want to observe, because we want to observe the pressure. We want to observe the temperature. We want to observe the specific volume inside of this container. What's going to happen with all of those properties, right, in the system. Now, here's the thing. As heat is transferred into the system, how are we going to transfer heat? Maybe by using the Bunsen burner or whatever method that we can use. Let's say we transfer heat into the system, right? So what is going to happen when we transfer heat into the system? Let's talk about this property, which is the temperature. What's going to happen with the temperature? Is the temperature going to increase? Is the temperature going to remain the same? Is temperature not going to increase? What's going to happen with the temperature? Now listen to me. For you to talk about the temperature, heat has nothing to do with increase in temperature or decrease in temperature whilst we have a system. What do I mean when I say that? If the system it is open, and then you put heat or you transfer heat into the system, like you would expect temperature to increase, right? Because when you heat something, temperature is rising. That's what you would expect. But if the system it is open, the temperature won't increase. It's either it is true the temperature can increase or a temperature can remain the same or the temperature can decrease if the system it is open. I want you to understand that, okay? Because you need to understand. So if the system it is open, the energy that's going to leave the system when we want to measure the temperature inside of the system, what if more energy leaves than energy that we give into the system? Therefore, the temperature in the system will decrease because more heat is being lost because the system is open. More heat is being lost, or the system, or more energy is being lost in the system. Therefore, less the temperature maybe could be less. So that does not mean the temperature will increase. Again, if the temperature if the system it is open and then we transfer heat into the system, we can maintain or control the system that the energy that leaves the temperature is the same as the energy that enters the temperature. Therefore, the temperature will be constant. You understand what I'm saying? So in this case, we have a closed system. So that means the temperature will increase. Undoubtedly, the temperature will increase as we transfer heat because the system it is closed, right? Nothing is escaping out of the system. So now the temperature will increase, right? So now what we also look at it is the specific volume. What will happen with the specific volume sharp? When we heat it, the temperature will rise, right? The temperature will rise as we heat the system, number one, because it is closed. Number two, what will happen with the specific volume? The specific volume will also increase, will slightly increase, not that much, meaning the volume of this liquid in here will slightly increase probably from there to there. But the thing is, what you need to know is that when the temperature increases, therefore the volume in the container will slightly increase. And the pressure will remain constant in this case because we are using the same pressure inside of this cylinder. Right? Right. So now we are increasing the temperature from 20 degrees 30 degrees, 40 degrees, right? We're increasing temperature, 50 degrees, 60 degrees, 70, 80, 90. But normally we know that this is liquid water, right? And then what is the boiling point of liquid water? We know that it's 100 degrees Celsius, but rather we will choose 99.6 degrees Celsius. So let's say when we heat the system, the temperature will increase from this state to that state, whereby we reach the boiling point. And then when we reach the boiling point, now we're going to have the equilibrium at some point of water vapor and liquid, right? So that means in this case, we're going to have the temperature of 99.6 degrees Celsius. But do not forget the pressure it is maintained. So meaning at the temperature of 99.6 degrees Celsius, there will be phase change again, okay? There will be phase change because look, here it is in the diagram, we can see there will be a phase change. So at this point, the temperature and pressure remain constant, but the specific volume will increase. So the pressure is the same, right? And therefore the temperature 99.6 degrees Celsius will remain constant for some quiet time. And then as it remains constant for some quiet time, there will be a vaporization, meaning vaporization. So vaporization, it is whereby at the surface of the liquid, there will be vapor rising at the surface of the liquid. That's what we mean by vaporization. It's boiling point, by the way, okay? So, so about that. So when the liquid has evaporated, what's going to happen? Further heating at the system will increase the temperature and specific volume, as we see here at diagram number C. But let me go back so that you don't get lost. What I want to do so that everything can make sense, I want to interlink you with this diagram and this graph over here so that you can understand, right? So the pressure is constant. Let me erase this one, which is 1 atm. Remember our pressure is 0.15 megapascals, right? So remember we started off with a temperature of 20 degrees. And then what did we do? we increase the temperature to about here, 99.6 degrees Celsius. This is our temperature. So I said to you, from this temperature to that temperature, there will be what? There will be what we call the phase change, meaning liquid will start to change into the gas. There will be phase change. That's the first thing that we're going to look at. And then I said to you, from diagram A to diagram B, as you increase the temperature, the specific volume increases. Okay, the specific volume meaning it is going to increase. Let's go back to this diagram. We can see on this side, on this axis of the diagram, we have the volume. So we can see that from here, which is 20, to there, which is the temperature of 99.6 degrees Celsius, there is a slight increase of the specific volume looking at this graph over here. So what I'm saying in this diagram, it correlates with what we see on this graph over here. It is the exact same thing, right? So that's what it is actually taking place. Now I want to jump to diagram C. So how do I jump from diagram B to diagram C? So now me jumping there, it is when we further increase the temperature, right? So when the liquid has evaporated, meaning we no longer have the liquid at all, now we have the water vapor, meaning we have the gaseous state. So meaning when the liquid has all evaporated, further heating of the system will increase the temperature and the specific volume. And then look at this, how volume it is. From here to here, we change. I mean, like the force, it is actually pushing this piston upward. So that means when the liquid water winds up, right, by increasing the temperature, the water vapor will start to show more than the liquid water, meaning from the liquid water to the water vapor, that's a complete sudden change of the state. And then the volume will most definitely be high. Look at the liquid volume, it's very less. Look at it's very, very high, right? So meaning we are looking at this point from here to here. It's when we have only liquid. And then you can just look at the water when it is what? It was at 20 degrees Celsius. And then you can look at the vapor when it is, look at um the deviation, the difference between these two numbers is very huge, right? Because you can understand that we are turning liquid into water vapor. So we're going to require more temperature to do that within a short period of time, so that in a closed system, we can increase our volume. In simple terms, that's how these graphs actually work, right? All right. So now, this is what I want us to understand. There are terms that are associated with what we see over here. For an example, the first term that I'm going to talk about, it is saturation temperature. So what is this saturation temperature? You see this diagram over here, it has a lot of information that you need to make sure that you understand. So when you talk about the saturation temperature, it is the temperature at which vaporization takes place at the given pressure, which is the pressure 0.1 megapascals, right? So when you talk about, I'll write it in short, we have what you call the saturation temperature. So when do we have the saturation temperature? Remember, I said to you that a vaporization will start to take place here at diagram number B, whereby the temperature is reached to be 99.6 degrees Celsius. So the saturation temperature, it is this temperature over here, whereby the vaporization takes place at the given pressure of a pressure of 0.1 megapascal. So when you define these words, you relate them to the pressure. So when you define saturation temperature, you relate it to pressure, relative to pressure. When you define saturation pressure, you relate it to temperature. There is saturation temperature, there is saturation pressure. So when you say saturation temperature, you say at given pressure. When you say saturation pressure, you say at given temperature. Okay, so how do we do that? Now, this is what I want you to understand. So We have water, right? And then I want us to talk about the saturation temperature. So meaning water at saturation temperature, meaning water at, I'll just say water at 99.6 degrees Celsius, right? The saturation, you see in relative, the saturation, what the saturation pressure is 0.1 megapascal. So at 19, you see, when you mention saturation pressure, make sure that you mention it in relative to temperature first. So meaning at this temperature, at given temperature, which is 99.6 degrees Celsius. Remember, by the way, this 20 degrees, it is not saturation temperature. So saturation temperature is going to be what? 99, because that's where vaporization starts to take place. Okay. And then again, when we talk about the saturation temperature, we're going to say at 0.1 megapascal at a given pressure, which is 0.1 megapascal, the saturation temperature is 99.6 degrees Celsius. You see, we use pressure and temperature to give one, vice versa. I hope that was clear what I have just explained over there. So the term that I have just introduced, it is saturation temperature and saturation pressure. So where do we find those? At diagram number B. So at saturation temperature and saturation pressure, what's happening with our pure substance? Our pure substance starts to evaporate, or vaporization starts to take place. That's what is happening at these two guys over here, saturation temperature and pressure. And in this case, for water, the pressure in this case is going to be 0.1, and then the temperature is going to be 99.6 degrees Celsius. Right. So what's the correlation? What's the relationship between saturation temperature and saturation pressure? What is the relationship between these two guys? Now, the relationship, it is defined by this graph that we see over here when I said it, that here we have the saturation pressure, and then here we have the saturation temperature. And then this graph over here, it is called the vapor pressure curve. Okay, for pure substance. It's called the vapor pressure curve, right? So now for this curve over here, this is the relationship between the pressure and the temperature. So this is how the curve actually looks like. Okay, all right. So now I'm looking at this term over here. It's called the compressed liquid. If we don't want to call it a compressed liquid, we can call it the subcooled liquid. That's another term that I want to introduce. So let me introduce that term. So we have the term that is called subcooled. That's how you write subcooled. Yes, I believe subcooled liquid. Or if you don't want to call it subcooled liquid, we can call it compressed liquid. We can call it compressed liquid. We can call it compressed liquid. So now, what is this term? What does this term mean? It's simple. Remember, we just spoke about the saturation temperature and saturation pressure, right? So, and then what is the temperature? Saturation temperature is 99.6 degrees Celsius. So what do we call a it's saturation temperature of this system, right? So now, of the liquid. So of the liquid. So if the liquid experiences a temperature that is below 99.6 degrees Celsius, what do we call that liquid? We call it subcooled liquid, or we call it the compressed liquid, meaning the liquid that has a temperature 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, 50, 60, 70, 80, as long as the liquid, it has that temperature, it is in possession of that temperature, we say that the liquid, which is pure substance, right? We say the pure substance exists as liquid. In that case, it is called the saturated liquid. Ne? The saturated liquid, it exists. Sorry, that this is I'll explain this later on. The saturated liquid, I'm confusing subcooled and compressed and saturated. I'll tell you. So, subcooled liquid, ne? It is the liquid that exists below this temperature, below 99.6 degrees Celsius, meaning this liquid over here, it is called subcooled liquid. And then this liquid over here, it is not called liquid water. We can't have liquid water, liquid water. This liquid water, it is called subcooled. But this liquid water, it is called saturated liquid. Why? Because it is beneath the temperature, saturated temperature. But below saturated temperature, we have subcooled liquid. So when we say subcooled, cooled means temperature. Compressed, we're going to talk about the pressure, but it is the same thing. So subcooled liquid, it simply means that it simply means that the temperature, it is lower than the saturated temperature for the given what? For the given pressure. Yes, don't forget. When you mention saturated temperature, you relate that to the pressure. That's how it works, okay? You relate that to pressure. So meaning subcooled liquid, it's for temperatures that are below 99.6 degrees Celsius. And then compressed liquid, it is the same thing. But when you talk about the compressed, now compressed, it's all about what? Compressed, it refers to okay, so I had a minor disturbance. I'm sorry about that. So the compressed liquid in this case, it implies to the pressure. Ne? I said subcooled, it implies to temperature, but it's the same thing, by the way. It is the liquid that is beneath, that is experiencing the temperature that is less than 99.6 in this case, which is the saturation temperature. So the compressed liquid in this case, we say which implies that the pressure is greater than the saturation pressure at given temperature. Compressed liquid, it talks about some the compressed liquid, ne? The compressed liquid, it talks about the pressure that is what? That is greater, should be greater, by the way. For pressure, it is greater. For temperature, it is less. Here we have lesser temperature than set temperature. And therefore, here we have greater pressure than set saturation pressure. Saturated temperature at given pressure. Saturation pressure at given temperature. That's how we say this. Yeah? Right. So, and then above, what is the fluid above 99.6 is water vapor, right? Or we can even say it's a dry saturated vapor. I'll explain that later on. So now in this case, now what we're going to look at is we're going to look at again diagram number B. Like I said, diagram number B, it has a lot. There's a lot in it. Should I erase? I just want to erase this part. Now, hopefully you took your notes. So now, in this case, once more again, so when this substance, which is our liquid water, it exists as liquid and a gas or a vapor, part of liquid and a part of the gas. Like I said, we have the saturation temperature. We say this pure substance inside of this system, this pure substance where it reaches this part and this part, we say its quality, listen to me, its quality is the what? It is the ratio of the mass of vapor, right, to the total mass. inside of the system. Listen to me. I'm saying to you, when at this part, whereby you see here we have interface, at this part, we have water vapor, we have liquid water, right? Therefore, what's the temperature here? Saturation temperature. So at this saturation temperature, with this pure substance, the quality of this pure substance, it is defined, the quality of this pure substance at this state, it is defined by the mass of the vapor to the mass total in the system. So the mass total, it will be given by the mass of the vapor plus the mass of the liquid, which is water, liquid. So in this case, what does the quality refers to? Quality refers to the mass fraction. Okay? Quality refers to the mass fraction. So that means, for an example, if we have water vapor to be the mass of water vapor, we started with 1 kg, right? So let's say mass of water vapor, it's 0.3 kg, and therefore the liquid will be 0.7 kg, right? So 0.3 kg, it refers to the mass of water vapor, and 0.7 kg refers to the mass of the liquid. So when we talk about the quality of water vapor at this point, we're going to say it's going to be 0.3, or you can say it's going to be 30%. And therefore the, what is this thing? Quality for water is going to be 0.7, or you can say it's going to be 70%, and all in all they make 100%, or one, which is the whole system of the pure substance, right? So now again, like I said, we have the dry. When I said I'll come back to it, we have the dry, what? Saturation vapor. What does it is? It just emphasizes on the quality. By the way, dry saturation vapor, it refers to the water vapor. Okay, remember, I said to you, this water vapor. I said to you, water vapor. It is basically the gaseous change from liquid water to water vapor. So we can say we have the dry, but normally just to use this term, dry saturation temperature, it emphasizes on the quality of the water vapor. So that's what it does. Okay. And then, yeah, and then we have what you call another, I think you're all familiar with this from thermodynamics 1, superheated. Superheated vapor. So when we talk about the superheated vapor, we are actually talking about the vapor at the temperature greater than the saturation temperature. So when you have the vapor, so now let's start it like this. Superheated vapor above this temperature. Supercooled liquid or compressed liquid below this temperature. Simple as that. Okay. So this is just the relationship between the pressure and the temperature, like I showed you there when we spoke about the saturation pressure and saturation temperature. And therefore, like I said, subcooled or compressed liquid means it's not about to vaporize. It's less than 99.62 degrees. Then here we have the saturated liquid. And then when the temperature, we let it, it is at equilibrium, it is increasing, we're gonna eventually have water vapor, and then we're gonna have the liquid. So here we have the mixed phase of liquid and solid equilibrium. And then when the temperature reaches this, whereby now we have the equilibrium, now we're gonna have what? We're gonna say, we say water vapor or saturated liquid vapor mixture. The temperature will stop rising until liquid is completely vaporized, right? It's a, oh, sorry, this is where we're gonna have that equilibrium line. This line over here, this line over here to there, right? And therefore, when the temperature is greater than this, now we have the superheated vapor, a vapor that is not about to condense. So meaning this vapor is far away to condense. Why? Because we call it a superheated vapor, meaning these gaseous molecules won't be able to form liquid once more again to condense. So that's what it actually means. And then when we meet again, now I will go through this beautiful diagram over here to explain it much more better, which is exact same. I can, by the way, I don't even have to explain it because having a look at this, okay, let me do it. We have this point there, we have this point there, we have this point there, we have this point there. So from A to B, it's a phase change, right? Liquid to gas, right? Remember that. Liquid to gas. And then here's that equilibrium, right? Which is this part that I've just read over here, whereby the temperature now will stop rising. The temperature is now constant. From B to C, the temperature it is constant. And therefore, from C to D, we are talking about the superheated vapor now. You understand? So that means here we still have the liquid, and then there we have the vapor, right? So that's what is basically happening. So what is this one? This one is when we increase the pressure. The pressure here was 0.1 megapascals, but when we increase pressure to 1 megapascal, what's going to happen when increase? I'll explain that later on, where we're going to look at the critical point. We're going to look at the supercritical point. We're going to talk about this line, which is PQ, which is above critical point, and so forth. And see you on the next, later on in the next session.